Hi everyone, welcome to this week's lecture, which is all about power and effect sizes. Major update, two major updates. One, I am cold. I've got gloves to the PD on. Hopefully that's okay. And two, maybe expecting coffee. I've switched to some herbal tea. So I'm a changed man, really, is what we're learning today. But today's lecture I'm very excited about because it really allows you to have the framework to critically analyze literature that you read. Now, arguably, all of the skills that you've learned in this course thus far help you critically analyze the literature. But particularly what we're going to talk about today, power, effect sizes, significance testing, these are some of the things which can commonly be misused or misunderstood and miscommunicated, and we'll look at examples of all of this. So I'm very excited for today's lecture. Hopefully you are too. Before we get stuck into today's lecture, let me give you an overview, which I sort of already did, but we'll talk about significance testing, inferential decision making, statistical power, effect sizes, confidence intervals, publication bias, academic integrity, and statistical method guidelines. And really, the thread that connects all of these topics is how we think about the results that we have in our experiments or in our studies, and how we communicate those results transparently to others and ensure that we're not misinterpreting what's there. So that's really the focus of what, or the undertone of what you're learning today, and that'll become clear as you see some of the examples. So we're going to do an overview of the significance testing, so the logic, the history, criticisms, decisions, and the practical significance. Is it a pun? I don't know if it's a pun, if it's the exact same word, but practical significance. So the logic is this: how many heads in a row would I need to throw before you would protest that something wasn't right? If I flipped a coin and I got two heads in a row, would you say that I'm doing something dubious or unfair? If I flipped it three more times and got three more heads, would you say that's okay? Or would you suspect something's going wrong? I did it 10 times, 20 times, 30 times, each time I'm getting heads. At what point would you say, hold on a minute, why are you wearing gloves today? Is there something going on? Is there something up your sleeve? Hopefully that is the critical thinking that I've instilled upon you. Not to, well, I was going to say not to doubt me, but it actually is very good to doubt me with your own justification. So, but in any case, doubting everyone and questioning the justification, questioning what you see around you. Many times, and you see this a lot in science, people do things a certain way, and if they're done for long enough, then often at times they can go unquestioned with the or may not be questioned to the same rigor as something that was newly developed or discovered. And what I hope you learn from this course is that that ability to critically think and question everything with appropriate justification is really the skill that allows you to navigate this space and also learn some very new things and interesting things. So here at this point, this is really the argument for statistics. At what point can you use statistics to help inform, perhaps in this case, your intuition that perhaps something isn't right here? So what we could do is, based on the statistical properties of sample data, we can extrapolate the probability of the observed relationships occurring in the target population. So we have our sample data that we collect. We look at what the statistical properties are of that sample data, and then we extrapolate that probability of the observed relationships occurring in the target population. Why don't we just recruit the target population? Typically, it's too large, it's not feasible, and so we require the process of sampling to allow us to make some inferences. And statistics tells us that the larger our sample, the closer our inferences can be to the target population, assuming that the sample is representative. It's randomly sampled, and it's representative of the target population. So in doing so, we're assuming that the sampled data is representative and that the data meets the assumptions associated with the inferential test. If you have a very, very large sample, but it's not representative or it's slightly skewed, you're unlikely to get results that mimic what you'd expect in the target population. So this is again is why I emphasize that assumptions are key to check as well when you're doing your analyses, because again, if you want your to be able to make inferences about your sample data and mapping onto the target population, then we need to ensure that the assumptions are met for those tests. So as a refresher or reminder of sort of introductory statistics language, the null hypothesis is typically considered as when there's no effect. What do we take as no effect for our example? And the alternative hypothesis is that there is an effect. And the logic of statistical testing is that you start by assuming the null hypothesis is true. So assuming that there's no effect, what is the likelihood of our data being observed under the null hypothesis? And so we have sort of a distribution, and we say, well, what is the likely if we have the, I don't know why I'm using hand gestures when I've created a very nice visual for you here. But hey, if you like my hand gestures, I'll keep it in as well. But we have our null hypothesis here, and we collect some data, and we want to see what's the likelihood of this test statistic, this data occurring, or this effect occurring under the null hypothesis. And if it's in the red zones, which is, in this case, it's 0.05, which is the typical threshold that we use. And so that's 0.025 at either tails of that distribution. If our test statistic falls somewhere in those boundaries, we say, well, the probability of us obtaining this sort of effect or this data under the null hypothesis is so unlikely that we reject the null hypothesis. Yeah. So yeah, we select a critical alpha value, which usually goes with 0.05. And this is the reasoning behind this is because a very, very long time ago, a statistician suggested that 0.05 would be a good threshold to use as a guiding, as just a starting point for understanding whether the observations or the effects that you see are likely under the null hypothesis. And since then, that has been taken by storm by every single researcher in all sorts of different disciplines, and there's a lot of argument as to whether that 0.05 threshold is necessarily appropriate in every single context, but often at times 0.05 is what's used for the alpha value. But it can change. You can make it to 0.01, you can make it to 0.1, but you'll see that when you read papers, more often than not, they use 0.05, or they talk about trying to have some sort of correction factor. And we'll talk about this in an example soon enough. And the correction allows for a more stringent p-value, like a 0.01 type p-value. So we start by assuming the null hypothesis is true, and then we evaluate how likely the observed data are under the null hypothesis. So remembering that the null hypothesis is that there's no effect. So if you have a directional hypothesis, you can use a one-tail test, and this increases power. We'll talk more about power a bit later in this lecture. But what that looks like in a one, see, this is a two-tailed test, because you can see the red is on both sides of the tail. If you have a directional hypothesis, you can move all of that to one side, and you'll have greater power for detecting an effect there. So what you do is you calculate the effect and its p-value to determine the likelihood of the null hypothesis in the target population. Is it bigger or smaller than the alpha value? If the p-value is smaller than 0.05, then we say that effect is statistically significant. There is less than 5% chance that the relationship is observed under the assumption that the null hypothesis is true, so we reject the null hypothesis. If it's bigger, then we fail to reject the null hypothesis. So all introductory statistics, p-value interpretations, but just emphasizing the logic here rather than really explaining what that means. So the logic being that it's under the null hypothesis that we're trying to work out whether the data that we see is likely or unlikely under the null hypothesis. So researchers tolerate some false positives, which is our critical alpha, to make a probability-based decision about the null hypothesis. We'll talk more about those false positives in a moment. But that's really, in a nutshell, the logic that's occurring. And this is the diagram that I've made here. So that this, when you're thinking of the null hypothesis, you really should be thinking of this sort of distribution. So, and the question is this: assuming our null hypothesis is true, how likely is our observed result? If it sits within this area here, then we fail to reject the null hypothesis. And if it's in these red areas, then we reject the null hypothesis. So here, the observed statistic, we find that the p-value places that less than 0.05, so it's in this area, and so we reject the null hypothesis. So what's the history of all of this? Well, it was developed by Ronald Fisher, and it was to determine which agricultural methods yielded greater output. Were variations in output between two plots attributable to chance or not? And this is really the fundamentals of when we talk about statistics. We get, like in the flipping coin and heads example, we're always asking the question, is this attributable to chance or is this not attributable to chance? And that's really the underpinning of it. If you recall back to the story I said in the first lecture about Fisher's exact test, and there was a lady who said that she could determine the taste of tea, whether it had milk poured first or milk poured last. And then he created a test where they had 10 cups of tea or 20 cups of tea, 10 which had milk first, 10 which had milk last, and she had to guess which ones had which, and they were randomly ordered. And really that was him trying to develop some assurance as to at what level would I be able to say, actually, she's not guessing. She has some skill here where she's able to drink the tea and determine whether there's a difference here. So agricultural research designs could not be fully experimental because natural variations such as weather and soil quality could not be fully controlled. That's really important because, as we know in terms of our research design, randomized control trials are probably they're not probably, they are the best form of evidence that we have for determining causality. So we can randomly allocate groups into two conditions. We could administer drugs in one and a placebo in another and nothing in the third if we want, and we could see what the effects are. And because we've randomly allocated that, maybe there's we've controlled from the controlling of factors has occurred through the design. But what Ronald Fisher discovered through this was, and which is why he developed this sort of thinking and testing, is that in all situations, this random allocation is not feasible. For example, in agricultural research designs. And so it was needed to determine whether variations in our dependent variable are attributable to our independent variable or likely due to chance. And so that's where all of this comes from. So significance testing spreads to other fields, including social sciences. And that spread was aided by the development of computers and training. I mean, think about when we've conducted our multiple linear regression analyses, exploratory factor analyses, it's literally clicks of a button to conduct it. You get a significance test and you can see the effects that are there. So it's very accessible to conduct this sort of testing. It became widely used during the second half of the 20th century, but so widely that used that in the latter 20th century it attracted critique for overuse and misuse. And we'll talk a lot about this in this lecture. Starting now. So the criticisms, we'll talk more as well later, but the main criticisms of significance testing, it was critiqued as early as the 1930s. Cohen's critique helped a critical mass of awareness to develop, and it led to changes in publication guidelines and teaching about over-reliance on significance testing and alternative and adjunct techniques. Now, even as you have gone through your degrees, some of the first things that you've probably learned is, what is the p-value? How do you interpret it? The significance test really underpins how you start learning about statistics. But what's important is that that's combined with an understanding of effect sizes, confidence intervals, all the things we'll talk about today, to understand the nuance of what that means in the context of what we're looking at. And so what are some of the criticisms? Well, the null hypothesis is really true. Think about it. If we were to take two random variables, what is the likelihood that there actually is no effect between them? If we take a correlation, say, between the two variables, what's the chance there's no effect? We've done analyses where we can see that any two variables are likely to have some form of relationship. Maybe it's 0.1, 0.2, 0.3, very modest relationships, but they exist. So saying that there is no effect is rarely true when we're looking at variables of interest. And significance testing provides a binary decision. So it's yes or no, but mostly we're interested in the size of the effect. How much of an effect is there? Now, coming back to that binary decision, that's often misinterpreted. If you ever read something, or hopefully not write something, but if you read something in research that says this is highly significant, or this is close to significant, or somewhat significant, none of that means anything. That actually is a misinterpretation of significance testing. Significance testing is binary. It either meets a threshold or passes that threshold or does not meet that threshold. So it's a yes or no categorization. There's no strength of a p-value. The p-value itself is just a threshold at which you can make this binary decision. And really what we're interested in is that size of the effect. And this is where it comes to statistical versus practical significance. And this is probably the number one thing that when you're reading papers, I read papers all the time that are missing this understanding of the nuance of, okay, it's statistically significant. Is that meaningful in the population? Or say it's not statistically significant, but what's the size of the effect that you found in your study? So they all need to be considered in conjunction to one another, because in some cases you may have a large size and effect. It's not statistically significant, but your sample size is not big enough to really detect an effect. So there's balances between the three. So significance is a function of effect size, sample size, and our alpha level, right? So statistical significance simply means that the observed effect, the relationship or differences, are unlikely to be due to chance, right? So all it means is that we reject the null hypothesis. Statistical significance can be evident for very small trivial effects if sample size or the critical alpha are large enough. And so really, that's an important point. Those 2 points are incredibly important. The first is that significance testing doesn't tell you anything about the alternative hypothesis. I said the alternative hypothesis is that there is an effect. But when you're doing significance testing, there's two options. One is that you reject the null hypothesis, so your p-value is less than 0.05, or you fail to reject the null hypothesis. But both of those inferences relate to the null hypothesis. Just because you reject the null hypothesis doesn't necessarily provide support for the effect that you think is there. It could be that there are many other effects that are happening, which are why we reject the null hypothesis here. So it doesn't lend support to the alternative hypothesis. Now, this is where many people flick to using a Bayesian framework, because the Bayesian framework says, how likely is our hypothesis given the data that we have? And then you start making claims specifically about your hypothesis and the probability of this hypothesis given the data. So it can be any hypothesis, and you assess the probability of it given data. For frequentist statistics, such as this, where we do significance testing, this is where we're focusing primarily on the null hypothesis. So do we have enough evidence to reject it or fail to reject it? Doesn't tell us anything about the alternative hypothesis, but people assume that, well, if we fail to reject the null hypothesis under these conditions, then they infer that the effect is there. But it's in any case, it's not about that specific alternative hypothesis. And the second point is in regards to sample size. If you have a sample size which is very, very big, very, very large, like say 500,000 or 100,000, doesn't have to be that large. It could be even smaller than that. You can sometimes detect statistically significant effects because you have quite a lot of power in your study design, but they may not be clinically meaningful. So let me give you an example of this, of sort of statistical significance, practical significance, and power. So practical significance is about whether an effect is large enough to be of value in a real world sense. Is the effect worth being concerned about? If I told you there was a significant effect between, say, coffee consumption and death, where there was a negative relationship between coffee consumption and death. And then I ask you a question such as, and it changes your attitudes and you're starting to drink herbal tea. And then I ask you a question and I say, actually, how many years sooner were those people to die if they drank 3 cups of coffee a day? And you say, oh, let me check the effect size. And you check the effect size. So actually, it was about 40 seconds sooner that they died. And when you look at that in the context of a lifespan, you know that is that really worth a behavioral change as a function of that small effect, even though it's maybe statistically significant? Is that effect size meaningful? Is it noticeable? Is it worthwhile to consider? This is really important, and the nuance that's missing in a lot of research discussions about this is when we consider our effects and the intervention of those effects, is it within the context of what is the meaning in day-to-day life? Does it have an effect that is something we should be concerned about or something we shouldn't be concerned about? The challenge is that this can be somewhat subjective, and this is where justification is so important. This is where, as a researcher, you need to say, I think this is clinically significant, clinically meaningful, for these reasons, and this is what we see. Or I think that this effect is statistically significant, but not clinically meaningful for these reasons. And so that's what we need to look into. So let me give you a story about all of this in a real world context. So I was interested in this question, looking at the relationship between hormone replacement therapy use and cognitive functioning in women, in addition to other measures like neuroimaging. But for this story, let's focus on cognitive functioning. And I was interested as to whether it depended on ApoE status. And I mentioned this study previous lectures in regards to moderation effects. I was curious to see, does the effect between hormone replacement therapy use and cognitive functioning depend on ApoE status? And ApoE is a gene, which we all have, and presence of the E4/E4 allele or E4/E3 allele puts people at higher risk for Alzheimer's disease. It's not deterministic, but it puts people at higher risk. And I did this study, and I found, in fact, there was no relationship between ApoE status, between hormone replacement therapy and the cognitive functioning as a function of ApoE status. So there was no interaction here. And I found that quite interesting, not necessarily the fact that the finding was null, but the fact of what that finding meant in the context of the research that was out there. So this study was done in the UK Biobank, a large population, a large cohort of over 500,000 participants. And why it was interesting to me was because here's a study published in Neurology, a top-tier journal, that looked at the exact same question in terms of the relationship between ApoE status and estrogen use or hormone replacement therapy and cognition. And they found there was an interaction between estrogen use and E4 presence on cognition. And they report the p-value there as being less than 0.05, so statistically significant. Then another paper looked at the same effect, and they found that ApoE hormone replacement therapy users had the highest delayed memory index score, and the p-value is 0.009 here for their interaction. So the interaction between ApoE and hormone replacement therapy was significant. Remembering that I couldn't find a statistically significant interaction for cognitive measures I looked at. And here's another study that looked at it and said we found suggestive interactions with ApoE status where the fastest rate of decline was observed among ApoE E4 carriers who were current hormone replacement therapy users. And this again is published in Neurobiology of Aging, a leading journal. Very, very difficult to publish research in these journals. And what I found interesting is that when you look at these papers closer, you find that actually the findings seem to align with what I found. And let me explain. So whilst in Yaf's study, the abstract says there was an interaction between hormone replacement therapy use and ApoE status. In the paper, it says there was an interaction between hormone replacement therapy and ApoE status and cognitive decline, and they report that p-value that we saw in the abstract. However, after adjusting, which just means controlling, for age, education, race, and stroke history, The interaction between ApoE and estrogen use remained, but lessened somewhat in statistical significance with a p-value of 0.06. Now, as I just said before, p-value is a binary threshold, 0.05. So it doesn't make sense to say it lessened in statistical significance. It either is or is not statistically significant. So what happened here is the authors adjusted, or they controlled for the effects of age, education, which, by the way, are the usual suspects to control for when you're looking at brain health measures, because we know they are related to age and education and cardiovascular history. And so when they control for these well-known variables, they found that there was no relationship. So the p-value was greater than 0.05. Yet in the abstract, they report the unadjusted model, the one that just has hormone replacement therapy use, ApoE, and cognitive decline. In the Sala paper, when you look at the table that looked at the effect, which showed a decrease in memory, you see the 0.009 that was reported in the abstract, but you see a little a next to that 0.009. And if you read the table underneath it, it says insignificant after FDR correction for multiple comparison. What does that mean? Well, in statistics, if you run this test over and over and over again, multiple tests, we fall into the problem of having the possibility of type 1 error. We'll talk about that in more detail later, but to give you an overview in this context, it's where you detect effects that otherwise are not there, but in some ways are an artifact of testing over and over. It inflates the chance that you'll detect an effect when it's not really there. And so what do we do? Because sometimes we're in a lot of the time in research, we're interested in many of the different comparisons, and we want to look at these subgroup analyses. So we apply a correction. There's a whole bunch of corrections out there. Fundamentally, what they do is they apply a stricter p-value to your analyses. So instead of 0.05, it may be 0.01 or 0.005 or whatnot. And it accounts for how many analyses you do, and it's its own sort of lecture in itself in terms of how you should consider what analyses you include. Is it just the analyses in your study? Is the analyses of all people who use that data set? But in any case, you control for that, and that gives you a more stringent p-value. And what these authors are showing with their A letter here is that, in fact, after they correct for multiple comparisons, which is conducting analyses over and over again, statistically, it's no longer significant. So it doesn't meet the threshold for that more stringent p-value, which is what you should be using. However, in the figure that's here, the ApoE HRT, so interaction, is noted in the figure without any mention of the not meeting the threshold after the adjustment for multiple correction. And so the finding is discussed here in the figure, and it's discussed in the abstract, but only in the table is it noted that it's in fact actually not significant after multiple comparisons. And again, in Kang's paper, if you were astute-eyed, you would have noticed that actually the p-value is greater than 0.05, and they describe it as a suggestive interaction. So in fact, it didn't meet the threshold for statistical significance. So in all three studies, they have found statistically that it in fact does not meet the threshold for statistical significance, but it's articulated in a way in which infers that actually there is an effect. And so when you look more deeper into the studies, you find that actually they align perfectly with what the findings are in this study. And so it doesn't appear that there's this interaction for cognition for these variables. Now, this is important because here are two links that you can look into that are focused on that Sala paper, which are published in the news that says hormone replacement therapy could cut Alzheimer's risk in some women, early study. Hormone replacement therapy could ward off Alzheimer's among at-risk women. Science Daily, BBC, reporting on this research paper, which in fact found that the effect was not there after multiple comparisons. So this is important. Science communication, it really matters. And it's something I'm passionate about. It's something that I do. So with every paper that I publish, I engage with the university's media team, and I try to translate that research to the public. And so here's one I did in relation to the dementia diagnostic timeline research. And there's an interview link there if you're interested in following it up. But I've also done pieces for the news where maybe I'm talking about a study, but maybe it's a bit complex. And I use that study as a way to emphasize some of these lessons, emphasize the when we hear findings in the news, how should we think about it critically? And what could be tangible for the public to understand, to critically analyze the research? And it's really the motivation for me to develop my own podcast. It's really a lot of self-promotion here. Sorry about it. But this is a podcast called Midnight Conversations, available on Spotify, iTunes, all your reputable stores. And it really was generated as a function of identifying this gap that, firstly, a lot of scientific articles that you may have encountered already are behind a paywall. And so that's even for you as a researcher, a student researcher at the university, there's still research that you can't access. For the general public, they can't access so much of the research without a university license or subscription. And so it's very inaccessible outside of the abstract. And so this podcast was a way for us to pick papers that were interesting to us, to allow us to translate that knowledge to the public in an accessible way, and embed some of these ideas of critical thinking and analysis in the public in a fun and engaging way on different topics. So that's really the focus of that, and that's really how I try to communicate science to the public, because I think the foundations of scientific thinking, statistical thinking, critical thinking are so important and will be the skills. They're the skills of today, but they'll be even more important as we progress in the future with AI, the skill of critical thinking. And we see it already in the news of what can we trust? What are the sources that we can trust? How do we think about the evidence that's being put forward to us? It all comes down to what we're learning about today: effect sizes, reading the literature, understanding what statistical significance actually means. And you can see in those case studies how this is just one example, this case study, but it's rampant everywhere. And you can pick up a paper and find this sort of discussion in there. And so the APA publication manual, Australian Psychological Association, they're very aware of these issues and have been for a long time, in 2001. So it made recommendations about including effect sizes, confidence intervals, and power. It's also somewhat mind-blowing to me to think that many years ago, people were able to publish papers with just a p-value. And I think it's incredible, and it speaks to the replication crisis that we have. And I'm getting ahead of myself. We'll talk about replication crisis later, but it's just amazing that that was it. And it's good that there's at least a bare minimum guideline here. And in 2009, they further strengthened the requirements to use null hypothesis significance testing as a starting point, but to also include effect sizes, confidence intervals, and talk about power. So APA guidelines are trying to encourage people to do so. And more often than not, reviewers, if you submit a paper or research to a journal, they'll ask for these things. They'll ask, if it's a good journal or a good reviewer, they will typically ask you to include your confidence intervals around your effect sizes. So historically, researchers in psychology have relied heavily on null hypothesis significance testing as a starting point for many, but not all, of its analytical approaches. APA stresses that null hypothesis significance testing is but a starting point, and that additional reporting such as effect size, confidence intervals, and extensive description are needed to convey the most complete meaning of the results. Complete reporting of all tested hypotheses and estimates of appropriate effect sizes and confidence intervals are the minimum expectations for all APA journals. So that came out in 2009. And so in terms of significance testing and p-values, the American Statistical Association statement on significance testing and p-values, and the links there for the paper, emphasize that p-values can indicate how incompatible the data are with a specified statistical model. They don't measure the probability that the studied hypothesis is true, or the probability that the data were produced by random chance alone. So this comes down to the idea of the alternative hypothesis. That's what people are really interested in. They're not really interested in seeing if they reject the null hypothesis or if they fail to reject the null hypothesis. They're interested in the alternative hypothesis. But the significance testing doesn't doesn't test the alternative hypothesis. And so that is where the Bayesian framework allows for a direct testing of whatever the hypothesis is. And so the problem as well is not in significance testing, it's in the interpretations of the results. And so when people think that when they're conducting a significance test and it's significant, it shows the effect that they're seeking to show, that is where, or the hypothesis that they're proposing, that's where the issues can arise. So scientific conclusions and business or policy decisions should not be based only on whether a p-value passes a specific threshold, because of what we said earlier in terms of you can have a p-value that's less than 0.05 and a really, really small effect. Or you can have a meaningful effect and a p-value of 0.051. Is that an effect that you would say is not significant? Statistically speaking, there's a threshold, and so it's not statistically significant. But this is where the interpretation matters, right? Is that a relation of the amount of data you've collected and the power you have to detect effects? So proper inference requires full reporting and transparency. A p-value or statistical significance does not measure the size of an effect or the importance of a result. So if your p-value is 0.00001, that does not mean that your effect is really, really strong and you have a highly significant result. It does not mean any of that. It just means that you're able to reject the null hypothesis, right? So your data is unlikely given the null hypothesis to be true. The p-value is binary. It doesn't indicate strength of effect. So how do you indicate strength of effect? We'll talk about effect sizes later. So, but keep that in your mind as a piece of the puzzle. By itself, a p-value does not provide a good measure of evidence regarding a model or a hypothesis. So what is a p-value for? Just saying, what is the likelihood or probability of us obtaining this data under the null hypothesis being true? And think of that distribution, right? Where does our test statistics sit under the null hypothesis being true, given our data? So what are the recommendations? Use traditional null hypothesis significance testing, but all with like Fisherian logic or inferential testing, but use complementary techniques. Always talk about p-values in the context of effect sizes and confidence intervals. It's a must and it needs to be done, so please ingrain it as you progress in your research careers, or even just critically thinking about research. Emphasize practical significance as well. So in addition to this, the next level is saying, okay, here's my effect size, here's my confidence interval, it's statistically significant. What does this mean? Is it clinically meaningful? There's so many times in the UK Biobank where they look at measures such as numeric memory, and that's how many digits they can remember on a scale of, I think, from 0 digits, they can't remember any, all the way to 12 digits. And sometimes you find people say, oh, numeric memory improved, it's statistically significant, or numeric memory decreased, it's statistically significant. And you look at the effect size, and they report 0.002. So 0.002 of a measure where the scale is 0, 1, 2, 3, 4. So it's so tiny that it's not even the difference between 1 or 2. A participant can't respond 1.5 or 1.002. They can only respond by getting one number correct or two numbers correct. So the effect size is so small, it's not even measurable on the scale that's being used. That's the use of some sort of logic to say, okay, the effect is statistically significant, but it's not clinically meaningful. Because if I was able to tell you, take this drug, it has all these terrible side effects, but it's statistically significant, your numeric memory will improve, I'm hoping you're going to ask the question, well, how much will it improve by? That's the effect size. And you'll be able to work out, is it worth the risk or not? And this is really the same thing when I think of hormone replacement therapy research. I think it's really important that the discussions are grounded within the framing of what does this mean to someone? What would you say to your mom or your sister or a friend who was interested in using hormone replacement therapy for the purposes of improving their cognition? Because they've heard research that indicates that. Look at the effect sizes, look at what the p-values really mean and in the context of what's happening. And that should be done for everything, not just drugs or medicines, but every single study needs to consider this approach. What does it mean for our friends? If we wouldn't recommend it for our friends and family, we shouldn't necessarily say it in our research papers. And that's just sort of the transparency I think is important. And we want to recognize the merits and shortcomings of each approach. So the summary of significance testing is that the logic we want to examine sample data to determine a p-value that represents the population with no effect or some effect. It is a bet at what point do you reject the null hypothesis, so that there's no difference there. So it was developed by Fisher for agricultural experiments in the early 20th century, and during the 1980s to 1990s, it was increasingly criticized for its overuse and misapplication. So again, it's all about the misapplication of the approach that I think that's the critical part here. The criticisms of it is that it's binary, but also it's not always interpreted in that way, but it should be. But it's binary, so that means that at the threshold barriers at 0.051 is deemed as non-significant, 0.049 is deemed as statistically significant, when in actuality, are they much the same? It depends on sample size, effect size, critical alpha, and you need to consider practical significance, because alone it's not intuitive or meaningful. Whenever you report a significance test for p-value, always report effect size and confidence intervals. Hopefully that message is clear and is remembered. So that's it. That's everything with significance testing. What we're going to do next is, well, we'll take a break. I'll have a sip of my tea, and we'll come back and talk about inferential decision making. See you in a moment.